presentation will be on the history of hydrogen fuel cells and current advancements. The way a fuel cell stack works is through a stack of individual cells that produce electricity. Each cell incorporates the use of an anode, a cathode, and an electrolyte layer. A hydrogen-composed gas such as natural gas or biogas can be used and will be entered into the cell along with oxygen to react and produce a current. These single cells are stacked to produce multiplied amounts of current to fit the power needs of the application. The benefits of this as compared to a battery are that the fuel cell will continue to produce electricity as long as the fuel or gas is introduced to it. The byproducts of fuel cell process include heat and water. The water is then expelled out of the exhaust where it is eventually evaporated and absorbed into the atmosphere. The first battery was created in 1799, known as the voltaic cell by Alessandro Volta. The principle of a fuel cell was first conceived by Humphrey Davy in 1801. It was then further developed into a working fuel cell by chemist William Robert Grove in 1839, known as the gas battery. Little progress was made after Grove created the first fuel cell as the parts were unstable and interest in the technology was reduced up until a spark of interest appeared in the mid-20th century. The first transportation vehicle ever powered by a fuel cell was made possible in 1959, by Harry Carl Lyric. The vehicle was an Allis-Chalmers farm tractor that was fitted with a fuel cell system designed by Cambridge engineering professor, Francis Bacon. The fuel cell was modified and produced 15 kilowatts of power. Allis-Chalmers gained interest in the technology and went on to partner with the United States Air Force to develop other fuel cell vehicles. These vehicles ranged from forklifts all the way up to underwater marine vessels. The first road-driven fuel cell-powered vehicle was developed and created by General Motors. The vehicle was a 1966 GMC Handyvan that GM suitably called the Electrovan. The vehicle utilized a Union Carbide fuel cell and used both liquid hydrogen and liquid oxygen for fuel. It was able to travel at speeds in excess of 70 miles per hour and had a range of 120 miles, which was quite promising for the time. The vehicle was shown off quite frequently at events but in end was not further developed due to its high costs to implement. Advancements are being made into a new technology called PEM. This stands for Proton Exchange Membrane Fuel Cell Technology. The advantages over current technology are the high power density that is offered as well as low emissions in the form of heat. If the technology is invested in, it could be mass-produced at a low cost. These cells function much like a conventional fuel cell. A negative and positive charge is placed across the membrane which creates positively charged protons to enter the membrane. The positively charged protons join with negatively charged oxygen which creates water. The water is expelled by the cathode and the reaction will begin again as a cycle. The 2015 Hyundai Tucson is a mid-size sport utility vehicle. The vehicle is being offered as part of a 3-year lease program to test the vehicle and gauge public interest in hydrogen fuel cell vehicles. Aside from its $500 per month lease and $3,000 down payment, the vehicle appears promising. With that price includes a government subsidy of $5,000 and free hydrogen fill-ups for the 3-year lease period. It has an operating range of 265 miles which cannot be touched by current battery-powered electric vehicles. Battery-powered electric vehicles require being charged after 50 miles of driving with a charge time of up to 8 hours. This Tucson can refuel its carbon fiber-wrapped fuel tank with hydrogen in roughly 10 minutes, making the driving experience much more comparable to what the public is used to. Toyota plans to introduce its new Mirai fuel cell-powered car later this year. Like the Tucson, the new Toyota Mirai will be leased out only in California, where its market is the largest due to the state's stringent push towards zero-emissions vehicles. The car was designed to look like nothing else currently on the market and it succeeded in that aspect much like the Prius. The car's AC electric motor produces 141 horsepower and 247 pound-feet of torque. The Mirai has a slightly dated nickel metal hydride battery similar to the Prius. This battery allows for regenerative braking and to also help with acceleration from a stop. The range of the Mirai exceeds the Tucson's operating range with roughly 300 miles of traveling per tank fill-up. Another advantage of the vehicle is that its tank stores 1.4 pounds less of hydrogen but can travel further, meaning it is more efficient and fill-up times for the fuel tank will be decreased by a few minutes. Hydrogen is the most plentiful element in the universe. It is in the air, water and all around, so why is it that the fuel source is not more commonly used? The issue that hydrogen production faces as compared to standard electricity is the cost entailed in the manufacturing process to acquire hydrogen. Current hydrogen reformation from steam is extremely inefficient, requiring roughly twice the amount of energy to produce when compared to electricity. When reformed from natural gas, 30% of the gas is wasted in reformation to produce the 70% hydrogen. The most cost-efficient method currently used to produce hydrogen is through steam hydrocarbon reforming. Steam hydrocarbon reforming is currently the most common method of producing hydrogen. Methane gas is introduced to steam at pressures of 3 to 25 bar at temperatures exceeding 700 degrees Celsius. This causes a chemical breakdown when a catalyst is introduced and yields hydrogen, carbon dioxide and carbon monoxide. The combination of gases is then reformed in a process called pressure swing absorption. This process rids the gas of carbon dioxide and other impurities, leaving almost pure hydrogen. This process accounts for 95% of current hydrogen production. Even as widely used as the process is, it is still not quite up to standard with other energy sources, such as using just pure natural gas. The newest and one of the most promising hydrogen production methods comes from the use of an artificial leaf that conducts photosynthesis and splits hydrogen from water. The research into this potential alternative fuel derived from bacteria is being conducted among faculty of Harvard University. Essentially, an artificial leaf is used to conduct the photosynthesis process from sunlight that will split water to create hydrogen and oxygen. A genetically modified bacterium can then be used to take the carbon dioxide and hydrogen and produce a liquid fuel called isopropanol. Isopropanol is also known as rubbing alcohol, which is a component in fuel cells. The leaf can produce 216 milligrams of the isopropanol for every liter of water. The efficiency of this process is similar to corn plants making kernels from the sunlight. A second alternative method of producing hydrogen is called electrolysis of water. The process of electrolysis essentially uses an electrical charge connected to two electrodes. These electrodes are submerged in water where the molecule will break into its two basic elements. Hydrogen will attach to negatively charged electrode and oxygen will attach to the negatively charged electrode. The amount of hydrogen to oxygen yielded is 2 to 1. Pure water actually requires more energy to complete the process. The water has a higher electrical efficiency when introduced to an electrolyte such as salt or an acid or base. This will reduce cycle time and increase efficiency. The process of electrolysis is a cleaner process than steam reformation and produces a much more pure hydrogen gas. In industrial applications that need pure hydrogen, this method is the preferred option. Thank you for viewing my presentation on hydrogen fuel cells.